generally about, as I said, precalculus, but specifically the problems will be the idea of functions. So we talked about that yesterday, the idea of functions, and given in a different way, operations on functions and graphs. That's pretty much it. So so before we continue with the sequences, let's do that. A quick review of this material. Pre-calculus, not this material, but rather at least this one piece of it, and that's the notion of the function, which is very hard to define, and you can put it in just 3 words definition, but that's not doesn't make things easier. So you don't have to really worry about that yet. It is more what this thing doesn't write T's. I've missed a few T's here. Current. So the whole little line disappears. Okay. Trends. He doesn't want trends. Anyway, so it's better to just have a vague understanding of what function is and then use it. Okay, so as long as you use it, okay, you don't really have to repeat that definition to anyone. So the function is just the correspondence between numbers. So even if one number is the input, the other one is the output. How you get from one to the other is irrelevant frequently. We are operating in a more abstract way, so it's not necessarily formula. Same applies to sequences as soon as we get back to it. But generally, this is something that you certainly have seen before. Relation between variables, one called the independent variable, the other one dependent variable. But it doesn't have to be a formula. What is the alternative way of representing functions?
By a graph.
By a graph, okay. What else? Was we saw yesterday, tables. Behind the graph, in fact, a table of values, say 1, 2, 3, 4, 5, 7. Okay, so let's not fool ourselves that practically speaking, the physical object, the graph, what is it? It's not a curve. It's made of dots. What we saw yesterday. If you did those dots closely to each other, it appears to be a curve. So that's every single software or Excel or it is the graphic calculator. That's how they do it. So behind it is a table of values. For each x, there is a y, and then you choose what axis you pick. But ultimately, these are the main ideas. 1, 2, 3, and certainly on the other hand, you can go from the formula to the table, and that's how you create the table. So it doesn't have to be there. There might be a table with no formula behind it. Okay, so when you give it a table, you know that's a function. Okay, so there is the fourth, if not the most important representation, and that is just a description, like an algorithm. So in other words, you tell the machine what to do with the number, what to do with x to produce y. So it could be simply like add, okay, words and nothing else. So there is no formula. You can produce a formula from it, but that is explicit enough. So this still counts as a function. And if you have this algorithm like that, add 2 to x. Okay, that's y. If you have that description, you can produce a table, right? You just take it's almost what happened here. Well, in this particular case, it was actually add 1 rather than 2. Oops. Okay, so as you can see, that's okay. Well, maybe it's okay. So add 2 to x, and the formula would be 3, 5, and 7. Okay. So you can have table from the formula. You can have a table where from the algorithm description rule. It could be like I mean, you don't have to do that anymore, but if you go take 10 years ago, you do your taxes. Okay? You have the input is your tax, I'm sorry, your income, taxable income, or just general income. You figure out with the rules, quite complicated, figure out going through this is deduction here, deduction there, and then you, at the end, that is why is your tax liability. Okay? So there is no formula there. There could be, you could produce a formula from such an algorithm, but it's not necessarily, it's not necessary. Okay? So in the meantime, from the table, wherever we pick to produce it, wherever it comes from, you could you plot the graph. Thirdly, remember the table that the data might come in the table to begin with. It doesn't have to come from formulas. Okay, so literally you have some kind of detect some scientific instrument that records, for example, temperature. Every minute it records temperature and put this and that's the time is the input and the temperature is the output. Okay, so there you have your new function. Okay, so let me carry this out specifically with itself. Well, let me carry this out first, the step that I just described. So this is how we would do it. X, I pick, say, -1, 0, 1, 2, and then I write here y equal x squared. Okay, and I write squared, -1 squared is equal to 1, 0 squared is equal to 0, 1 squared is equal to 1, 2 squared is equal to 4. Okay, so then my table is, once all the computations have been carried out, I have -1, 1, 0, 0, 1, 1, 1, 1, and 2, 2, 4. Okay, so and then these are the points for me to plot. Okay, so these 1, 2, 3. These are at least 4 points I would plot on the xy plane, and well, where are they? So 0, -1, 1 over here, then 0, 0, then 1, 1, and 2, 4 here somewhere. Okay, so this is 2, and this is 4. So that's the xy plane, and this is what you have done previously in courses like college algebra. So this looks familiar, right? Okay, so just a quick review, and you should be able to plot graphs by point, as I just did, with the possibility of well, if you have those 4 points, what's the next step?
To continue the graph?
No, can you be more specific?
To find the equation from the 4 points so that you can know the entire graph?
Well, that is actually quite a challenging problem. If you have points and you want to find a formula, that is certainly a legitimate question. So you have the data and you want to know if there is if you do in science, for example, you have instruments, you derive some data, and there seem to be forming some kind of curve, and then you want to figure out what the formula of that curve is. That is, and so you're looking for a pattern, you're looking for a law of nature, and you might or might not be able to find it. So that's a challenging problem. When I'm talking about this, it's something simple. Just actually recognize the curve from points. And if you have too few points, as I do, it might be there might be some a little bit of a challenge, but really not a big one like this. So if you cannot recognize the curve, and then what do? You get 1 points. So this curve is, what does it look like?
Correct.
It's a parabola, yeah. So that's as long as you recognize the parabola, you know roughly what it behaves like, and you have your ideas right here. So now let's do the same with Excel, which allows us not to have instantly more than just 4 points, and then there's all kinds of advantages of it. So the data might be then of any magnitude. So let's, and I'm doing it from scratch, so a more extensive, more complicated spreadsheet you saw yesterday, okay? But it is just, they don't appear by magic. You could, however, start from scratch and build it little by little, and every time I will show you how it is done, so that when time comes, projects, remember, then we would be, you can do. Okay, so all I want to do right now is this function, which we did very by hand, these 4 points, and I want the full graph. Okay, so certainly graphic calculator will do it for you. The problem with the graphic calculator, the whole process is inside and you don't see what's happening. Okay, so it's a little bit too like magic. The Excel, however, it plots it point by point, and each point will be visible. Okay, so each row will be simply a point on the graph. Okay, so let's just do it. So number 1, which you always pick, you may have seen it, it is the interval of the independent variable. By how much we're gonna say 0.1, by how much we're gonna progress along the column of independent values. So because here I do it by hand, I chose it to be 1. Okay, so I progress from -1 to 0 to 1 to 2 because I don't want to do this too many times by hand. But that's what the spreadsheet can do for you. It is much easier. So I put x here and y there. Y is equal to x squared. This is probably okay. Just to remind us what the formula is. Suppose I want to start x just as in this table. I'll start with -1. So the first value of x is -1, and then what I'm going to do is I will progress from -1 at the rate of 0.1 at a time. Okay. So have you seen Excel before?
Yeah.
Yeah. So who said yes? Okay. So did you use any formulas?
Those simple ones. We did in our
Well, we'll start with very simple. I mean, x squared. It's not the hard one.
freshman engineering class or whatever.
Okay. So learning Excel is worthwhile. That's something I'm going to tell you. So it is easy to learn and it is worthwhile. I mean, if you want to do any kind of numerical practical applications, the only alternative is to learn actual programming, and that is a challenge. And it's pretty much usually an extra class you have to take, and then it is a bigger challenge than that. In the meantime, if you go to Wall Street, for the most part, they use Excel as the main instrument because programming is hard, and this one is easy enough and it is easy to visualize. Also, in every like office in the country and elsewhere, there is thousands of secretaries are using Excel. So, which people who may or may not have a high education. So it's totally learnable, as you can see, you're going to see in a minute. But the formulas have to be done, and it does take some extra thinking. So that's what we're going to do right now. So what we do is the very first step, how to use the formula. We want to, the computation is very simple. I want to have -1 plus 0.1. Okay, so but what I do is I want to make a reference to the previous value so that I want to write a formula there rather than the answer so that I can then spread this formula down. It's a spreadsheet, and so that I have to do it once, but I have to do it right. So here's what I do. I have to add 0.1 to -1. So I click on the previous cell. The previous value of x, which just happens to be -1, but then it will work with everyone. So you can see what has appeared, R-1C. You know what it means?
Each row, same column.
That's right. The previous row, -1, and same column C. Okay, so this is called a relative reference. Relative, wherever you are, the reference will be to the previous row, same column. Okay, it is, however, now we want to add H, that 0.1. Here, the reference has to be absolute. So not -1, you just have to say exactly what the row is, the R, and what's the row? 2, and column? 1. Okay, see? So the formula is very nicely colored here. So you see I'm referring to the previous row, as well as that in red to the value of H.1. Okay? So I push enter. The formula has been entered, and as you can see, I progress from -1 to 0.9. Okay? And then that's a good thing, because if we did the formula correctly, I could just spread it down, and I will have that formula appearing, computing this more and more. So let me make it so it would look nicer. Okay, I will make numbers. Okay, right. So from -1, -0.9, -0.8, and so on. Okay, so this way we have the 1 by x values. X values are going to be taken care of, even though we only go to 0.1, well, that's okay for start. Now, how are we going to compute y's? We'll be referring to the corresponding value of x. So once again, this formula always starts with equal sign. Okay, so what do I do here?
Column 2.
Yeah, I could just click. So RC -1 means same row, previous column. Okay, so and you can see it's highlighted in blue, so you know RC -1 refers to the previous cell. Okay, and then what do I do? I square. Okay, and I have my answer. Okay, so then once again I highlight down, so I start with the formula that we already have taken care of, and now I want to have this formula repeated in every row below, every cell below. Okay, so I will have then I push control down, control D, which stands for control down, and then a bunch of values of y have been computed. Okay, so that's how you produce a table of values for a function. As long as you have a formula, it doesn't matter the complexity of the formula, doesn't matter. You will produce a table of values in this manner. I could put that formula to be of any complexity you can imagine, and it will if you do one formula correctly, you can have as many values as you want by doing this spread. Okay, so let me show again. So this one is referring to I'm picking the right random cell. It refers to the previous cell in the same column and add value of h over there. Okay, on the other hand, if I pick this value, as you can see, it simply takes the value as the input, that 0.1 on the left, and squares it. Okay. Okay, so that's your table of values of the function. That's how it's done. From yesterday, remember the simulation? It's pretty much does exactly the same way. We're using the plotting. So how do we plot? And there are a number of ways to plot it in Excel, but I prefer the scatter plot. So you highlight this, and you go to Insert, and you click, and there's a bunch of possible charts. This is scatter plot. So there are all kinds of bars and pie charts. They're not very applicable to mathematics, but scatter plots are especially applicable. So you could choose this. This is literally what we know about. This is literally what we see on the left. We have like 20 points or so, and at every point you can see those 20 points on the left. Okay. However, if you want to fool somebody, you can choose this one. Excel, the thing is, Excel does not know the formula that we entered, or the data on the left is the only thing that Excel knows. But it encapsulates in this manner, like this. So it takes all of those points and connect them by the first, which we just did a minute ago ourselves. We looked at those 4 points and thought it looks like a parabola, so let's interpolate as well as extrapolate beyond. They don't do extrapolation as much, only interpolation. But once again, if you want a pure curve, very nice usually, but you are sort of fooling yourself about the nature of the curve. I prefer this one most of the time, or this one is just fine. Reminds you that what you're looking at is indeed just the table of values. It's not actually the formula y squared is not there. So hypothetically, between say 0 and 0.1, something may have happened, and there is no record. Maybe it jumps up. Okay, so there are limitations of any kind of numerical analysis of functions as well as data visualization is something that we cannot resolve by visualization. So, but that's what studying functions and calculus will help us with. So we will know that indeed it is this picture is indeed true. This is the problem. You can see that it is. But let's do it this way for now. Okay, so that's something hopefully not that look too complicated. or challenging, just you do it a few times and you will know how to do it for the rest of your life. What we want to do here is something else, and that is beyond this. As we progress with calculus, we were studying functions. We don't study one function at a time anymore. Okay, what we study all functions up together anyway. And that if you take all the functions, well, either a lot of them, obviously, we want to have some kind of structure. And the structure is algebraic operations. So functions can be added, subtract, multiply, and divided. And what's the fifth operation? No, not exactly. If you have two functions, if you can combine them by the four algebraic operations are operations and numbers, right? And so because of that, you can also combine functions in that manner. Okay, but there is a fifth operation that only applies to functions.
Inverse.
Well, you're going in the right direction. The word is the composition. Remember, you can combine two functions. So we'll see that in a minute. And there's one problem that nature as well as the inverses will also come up in the upcoming moment. Okay, so let's do a little bit of that. And what I'm going to do is I'll just push this aside a little bit. Just remember that this is the function, and I'll create a new function. Okay. Usually it's not hard once you learn how to copy and paste. You have a bunch of functions. So the second function, I don't know what function do you like? How about sine? Why not? That doesn't make any difference. So sine x. Okay. So this cell certainly does not produce the formula. You have to actually do the formula, but once you did it once, you can guess what I'm supposed to do here. I don't even have to highlight anymore. I just erase square because we're not going to do square anymore, and I just write sine. So what do I write sine? And what's next? Parentheses. So as you can see, parentheses at the beginning and the end, so that it is clear that we're talking about the function sine. And then the input is inside the parentheses. Okay. So x squared, there are no parentheses, but it's the same thing. Okay. So those parentheses certainly will come up. Okay. Okay. So that's the table of values of sine. I could also do this thing. I'll go now. I will also chart it. Insert. Once again, I will insert a chart like this. Okay. To distinguish, let me make them small and push them, move them around a little bit. So this one is the first function, and this one is the second function. Okay. Okay, so you can see how the behaviors are different. They both start at -1, however. And now I could produce a new function from these two. Okay, so I want to add them. So there are algebraic operations. Number one operation is addition. So if we once you think of functions as tables of values, what values of numbers. So it's tables of numbers. So if you can add numbers, you can add functions by using the values of the function. So suppose here I have x, and I want to plot y equal x squared plus sine x. Okay. Okay. So let's figure it out. What do I put here?
-1.
That's right. I could put -1 physically, or I could copy. Do you notice that the counts, the input counts are the same for the two functions? So for the first function, the input is also the same. Okay, so I instead of doing it from scratch again, I'll just copy. So I'll like equal this one. Okay, and that way I can quickly create the input values, the input column. Okay, So, okay, so I do have a formula, now for y. I have a formula, I could do it the way we did it with with these two functions, so that's not a challenge. The challenge is to see that we don't have to compute sine again, it's been computed already, okay? And I don't have to square x, this is the x on the left. I don't have to square x, it's been done already. So what do I do? Equal what? No. I want to recycle the data. These two functions produce new data. Okay, I don't want to carry out those computations again. I will just recycle. So
Column 3 plus column 6.
column 3, but that's roughly what's supposed to happen. So I just click. I want this value, and I want to add that value. Okay. So I take the outputs. The inputs are already taken care of, right? It's the same input. And now I take the two outputs, one for x squared, the other for sine, the other for okay? So add it together, and once again, I have all my formulas right here. Okay, and so once again, I could plot it if I want to. You can probably predict what the graph looks like. So this is the sum. It is mostly dominated by, I suppose it's mostly dominated by the parabola on the left rather than, unfortunately, what Excel doesn't do, it doesn't keep things straight in terms of, it resizes the window. So it is kind of a bit disproportional. So this chart, as you can see, doesn't match exactly the size. Well, this, yeah, it's, hold on a second, I should have, yeah, it's actually wider. So if you want to match like this, okay, the values are even more like this. Okay, so the magnitude of y's for the first function for the second, they are not quite correctly visualized, but that's okay. So then we have a new function. New function. This is the sum of the two functions. So it still looks like a parabola, but as you can see, there is a dip below the x-axis that been introduced on the left, so it doesn't make a difference. Why does it go below the x-axis on the left? The third graph.
Because of the negative numbers.
Yes, because we're adding negative numbers here, there are negative numbers for the sum. Okay. So that's the sum. What do I do to get I can now combine these two functions in any manner I want, including I could replace this plus with minus. I could replace minus with multiplication. So let's do both quickly. So I put minus here, and well, that certainly changes the picture. Okay. No, that's the difference. Nothing really special. Now we produce these in a very fast manner. The multiplication will look probably stranger. Okay, so if I want to multiply, okay. So as you can see, the positive negative, the change from negative to positive of the sine function, the second one, does affect the outcome very dramatically. Even though the rest of the graph appears to be like a parabola here, parabola there, right? But if you continue on with the signs, with more axes, then you'll see the more weird indicator. For example, I could change h to make a step larger. If I make this step larger, say 0.2, we'll see more interesting behaviors. You see what's happening. The product of the two functions eventually goes back because that's what sine does. It goes back down and it will cross the x-axis again, becomes negative. So and there the product will behave in that manner. So anyway, so that is not really the biggest challenge typically that we encounter. The typical challenge that's the next work is the composition. The composition is much more challenging, and it is in fact so much so that it is a bit hard to visualize with Excel. So these two functions are not they're just on the slide sort of. So first of all, what is the composition? Do you remember any examples? Compositions of the functions?
Not exactly sure what you're trying to ask.
Well, if you remember the word composition.
Not in this context. I think let's take a break, 5-minute break. So we have 75-minute class, so we'll take around this time. If we take 5-minute break, we'll have 35 more minutes left. Okay, so 5-minute break. Unless you don't need a break. You don't need a break? Okay, well, let's continue on. Compositions. Compositions are very important. I mean, they're more important later than now. Before calculus, they're less important. And there's less and less algebra of what we just done. This is the composition. Just to refresh your memory, you see two functions, right? And they are composed. They are combined to a composition. Does this look familiar? That's just a combination of x. Well, actually, that should be 3 different functions, wouldn't it? It'd be the square root of x, then also x squared, then also x minus 1.
You could, yes. But the why make things too complicated? Let's have two functions to keep it easier. So in case you haven't faced this problem before, the issue is to recognize that there's a composition there. Is that the things have to be, unlike what we just did, things are computed consecutively. Things are computed consecutively, unlike, once again, if we go here, you have one function, you have the other function. You can compute one function and the other function simultaneously, and then they're combined, and there's one value at a time. So, for example, I pick the value, I do this now, I just go row by row. So I can have, if I need to know the value of that new function at x equals -0.2, what do? I could just compute the value of the first function and the second function, and then add them together, and there is no trouble whatsoever. I don't need anything else. The rest of the don't have to exist. The rest of the value interest, there is no interest whatsoever about the rest of the values of these functions. If we're talking about compositions, that's not the case. If we look at this formula again, as you can see, there is indeed, it is x squared minus 1, then let's say that's our second function. The second function is square root. You cannot apply the square root until you already know the output of the first function. Okay, so if you want to write it out in 2 steps. Step 1, square x, subtract 1. Okay? Step 2, take the square root all the way out. Okay, so that's a 2-step procedure. You cannot proceed to step 2 until you're done with step 1. Okay, so and you will look at it if you want to do pre-computation like the way we did it here. Right, we computed all necessary values for the first function, all necessary values for the second function, and then we produce the third. This one is very challenging. There is no alignment along the x-axis. So, for example, let me try to give you an example on this one, which would reveal the complexity of what we're dealing with. Suppose I want to do a composition, but if we just take this function, these two functions, rather than what I just had, this is what we're talking about. Yeah, I'll stick with that example. When I have y equal sine of x squared. X squared. Okay. Yeah. So one function sine, step one, square x. Okay. Step two, take sine. All the outcome. Okay. So let's compute using this data. Copy this. Okay. So suppose what I want to compute. So let me kill this. What I want to compute is sine of x squared, that new function which we don't have yet, and I want to compute, say, x is equal to. Hold on a second. 0. Let's see. So if x is equal to 0, then this is where we're 0. Here 0. Okay, so this is sine 0 squared is 0. Okay. Well, it's a bad example. Okay, let me take something else. Okay, let's take negative 1. So negative 1 squared is 1, and then the trouble is my output is equal to 1. What piece of information in this function do I need to use now? So previously we just did this. We proceeded 1 to negative 1, negative 1 to 1, negative 1 to 0.04, and then together that we have the output right here. Okay. Now, but it's not going to happen if we're talking about compositions. So what part of the second function do I need to use to compute what I want, the composition? So I want sine of x squared.
You look for your output in the output column of the next one. So you'd be looking.
That's right. You look for the output 1. See the output over there. I'm looking for that value in the input column of the second function. So here it is. You see the problem? They're not aligned anymore, so I have to progress. I progress from x to y, and only once I've done it, I know where I'm going to be with the second function. So I ended up with negative 1 goes to 0.4. So the answer is 0.84. Okay, so that's why the spreadsheet does not work easily. You can actually carry out that operation with the spreadsheet, but you have to carry out more advanced operations such as search. You have to, the second operation, if you want to do it yourself, you would have to search for the first column of the second function, okay, x, to find 1, which we just did very easily because there's so little data. But imagine that it is a long spreadsheet, then you have to actually ask the computer to do it, and then with that, then you should be able to compute the rest of the function. Without it, we cannot just go proceed from left to right, compute everything as we did with the addition, subtraction, multiplication, or division. The division, the only complication is you might divide by 0, but otherwise it's exactly the same. So, okay, so that is the challenge. The spreadsheet doesn't help a lot with compositions. And this I believe that this does help, and it is thinking of functions as algorithms, and if you can split it into 2 or more consecutive steps, that is a composition. It is better probably to do it in a more explicit terms and actually introduce extra variable, the halfway between the first and second step. Suppose we have an extra variable, intermediate disposable variable, let's call it u. So still the original input is x, the output is u, okay, and I just read the first row, square x subtract 1, so u is equal to x squared minus 1, okay, and then the u becomes the input of the second function. Okay, so what do I write here?
It's u equals square root.
Not u, y.
Square root.
Y equals square root of u. Okay? So once this is done, the verbal description is the steps, okay? The algebraic description is on the right. So you can analyze this. You split the function into two simple steps, just the way we did it elsewhere. And you see how easy it is, however, to compose it back. So that the challenge was how to get from here to there was it is in decomposition. So you have one function, break it into two, and if you represent it as decomposition, that's what we do have. However, the backwards is easy. How do I get from these two steps back here? These two steps, two formulas. U equals x squared minus 1, and y is equal to square root of u. How do I get the original formula?
Did you replace the U?
Yeah, just substitute u into the first formula for u, substitute the second, and you have the formula. So the decomposition is the challenge. Okay, so this one, the second one example is simpler because I simply have u equal to square root of that's supposed to be x, square root of x. Okay, and the second step is sine y equals sine u, right? Okay, once again, substitute u into x, we have the formula back. So that's the easy part. So the word composition is actually easy. So when the problem is given to functions, compute the composition, it's usually very straightforward substitution. Decomposition, or in other words, represent the function as the composition of two unknown functions. That's a bigger challenge.
No.
Yes.
You mean x squared, not square root of x, right?
Yes. Yeah. Well, thank you. Yeah. Fix that. Okay, so, and there's certainly no challenge computing the function as it is given with the spreadsheet, but computing it, let's do that once anyway, because it's not easy to do it with the composition, with the spreadsheet, so let's do it without the spreadsheet. But this time I'll put the variables in the correct place. So I'll put x here, u there, and this time we don't have formulas. Say I have 1, 2, 3, 4, 5, 6. 0, 1, 2, 5, 0, -1. Okay, and here I have u and y. Okay, so two functions. And let's say u's are 0, 1, -1, 0, 1, 2, 3, 4, and 5. Okay, the outputs are say -1, 1, 2, 5, -1, 0. Okay, so these are the two functions given by the tables. But this time, if I want to compute, so remember sometimes we give these functions names. So the first function is f, and in other words, we have x equal f of u. Okay, hold on a second, the opposite. U is equal to f of x, right? In independent versus dependent variables. For the second row, it is y is equal to g of x. Once again, there is no formula. I made up the numbers, so the function exists as a table carrier. Okay, and so now suppose I want to compute. Well, first of all, remember the notation for the compositions. F composition G, or rather G composition F.
That would be F O G.
Say it again.
F, then you put a small O.
Yeah.
G.
Oh, I didn't know that you can say O. Yes. So first of all, the order it reads from right to left, unfortunately. So it will be G comes second. So like this. Okay. So that's the name of the new function. So the name of the first function is f, name of the second function is g, then the name of the new function f, o, g, that little circle. Okay? So I even put a circle here.
Okay, so one function composed with the other function with the order matters, right? Unlike additional order matters, so you progress from first compute F, then G. So let me compute a little. So how about it's called H? What is the this? What is the independent variable of my new function?
H.
No, H is the name of the new function. Well, look at the examples above. These are on the left are the compositions that when the work has been done. Okay, the new variable is nothing but a disposable tool. So it's like you would have a paper, write it down, then you use it, and then you throw it out. Okay, so the dependent variable is x, the dependent variable is y. Okay, so we'll be getting from x to y through u. Okay, so for example, if I start with, so which means that probably I should take the column or x column from the very beginning. Okay, so I'll pick 1, 2, 3, 4, 5, 6. Okay, and now let's start computing. Okay, so I go from 1 to 0, and then from 0 I go to 0. You see, I'm going to the next different row. And then I apply the second function, and the result is 1. Well, I asked you what compositions are, and I think that we didn't discuss that enough to actually why do we care about compositions, and they really exist only in mathematics. So if anybody remembers examples of compositions outside of something specific, real life applications.
The language, like if you're translating from one language to another, like the spoken
That
language.
is totally, except it's not about numbers, but the logic applies totally. So you apply from a language, from French to English, or from English to Spanish. Okay, then the result is translation from French to Spanish. If you want a country, take instead currencies. So from say euro to dollars, from dollars to pesos. Okay, so the result is from euros to pesos. Okay, so any kind of change of units or trading one thing to another will be resulting in as if you're skipping that intermediate step. Some people you can think of say I don't know cattle on the left and corn on the right. In the middle, what's in the middle? Money, right? You exchange cattle for money, then with that money buy corn. Okay, so that's a composition. And if there are prices there, you will, if you know how many the price of the cattle per whatever in dollars, and you know the price of corn in dollars, then you can combine them together, and you will know the relative value of corn in terms of cattle. Okay, so the compositions are throughout there everywhere, and then as you can see, you don't have to. The example is very good with the languages because it indicates that you don't really care about numbers as much. You don't have to care about numbers. The other operations with functions are important. The algebra important is addition, subtraction, multiplication, division. But with composition, there it's much more general. I think it's even more common than anything else. So we just studying things that are quantitative and their numbers. But the composition will become more and more important as we proceed. So okay, so one. So what do I put in the first row? The input is 1, 1. Output is 1. Okay, let's do it one more time. If I start with 2, I go to 1. Oops. And from 1 I find 1. Okay? I have more colors here. Okay. Read. From 3 to 2, from 2 to 5, they just happen to be aligned accidentally. But then I put 5 here. And okay, from 4 to 5, from 5 to, here's where it is in fact 1. Okay, and two more. We have 5.0, 0.02, and you can see the arrows might come together. Do you remember the term? Related term?
Converge.
No. The two, as you can see, two if you look at the red arrow and the yellow arrow, the function f has this property that the two different inputs produce the same output, 0. Remember what property it's related to? Or what property violated here?
Because they have the same output, it's
Yeah.
not a function.
No, it is a function. The function, as long as there is no, I mean, if you're thinking back, if you go backwards, then when you are not allowed to have this. Okay, but this is okay. So, anybody remembers what it's called? Well, the not being a function, there's a test point, it's called the vertical line test, which is what you're referring to. This is the polynomial line test. So, the two different values produce the same, two different axes produce the same one. Well, same view, okay? When it is the case, we say the function is not one-to-one. Remember that term? One-to-one. So this function is not one-to-one, and we can see that with the arrows. And if we follow the yellow line, then we have here 1 again. Well, we actually have 3 of them. So because the second function is also not one-to-one. Okay, one last left. So from 6 to -1 over here, and it is -1. Okay, so that's my new function. So these are compositions. So that was a good thing that we ran into the issue of function being or not being one-to-one, and why is it important if you remember being one-to-one and not being one-to-one? Well, if you can convert dollars into pesos, you might want to convert pesos into dollars. Or maybe it's like measurements of clothing or shoes in different countries. They are different. Once again, you convert back and forth. And or Fahrenheit in Celsius. Miles and kilometers, or miles and feet. Okay, so they convert back and forth. Those formulas go back. But look at the first function. If I can convert x into y, can I convert u into x?
If multiple different values turn into the exact same thing in the end, it's hard to take that same values and send multiple ones at the same exact one.
That's right. So if you want to revert it, then the second column becomes the input, and the first column becomes the output. And we want to reverse the arrows and look at what happens if I try to reverse the arrows. What happens to 0? It will have 2 arrows. Well, let's try it. We can do it literally. To examine what's going to happen. So if we revert and I put u and x, okay, so I will put, let's pick a few values of x, because this function I want to arrange it in a more or less consistent way. Maybe 1, 0, 1, 2, 3, and 4. And I'm reversing the arrows. So -1 goes to 6, and 0 goes to 1. But it also goes to 5, right? Reversing arrows. So the red arrow goes 1 goes to 0, and then the other arrow 5 goes to 0. So which is still a function. That's not a problem. It's like you square -1, you square 1. It's the same output. That's not a problem. But when you try to reverse, for example, you do a square root, you have trouble because it's what if it is negative? So, so anyway, so 0 goes to 1 or 5, which means that it is something that is not allowed. And so the conclusion is, what's the conclusion indeed about this new table that we're trying to produce?
That the reverse is not a function.
The word, that's right, there was inverse, but yes, it is not a function. And so what is, should be an explanation for you. Okay. Okay. And that this is what we're trying to accomplish is to find the inverse. So the function has to be one-to-one for it to have the inverse. So with the number sets illustrated here, how those arrows can't reverse. But there are other issues that will come up later. I'm going to go into inverses 2 to 4 beyond the basic idea. But once you start plotting graphs, things happen to the when you find the inverse. What happens to the graph, if you remember?
It flips above the origin.
No, not above the diagonal. So it does this thing. Okay. Above the origin would be like, hold on a second, like, something, well, with a chart. I don't know what it's like. It's like in my heart, but it's probably easier to just, so like this and like that. That would be flip around the origin. And in either it looks like more like this. So if this is the diagonal, you flip something like this. So we'll talk more about that. This time we're looking at the basics, and but you need to review probably this stuff even before you get to the homework. So you can either I do believe that it is in the for the book. So just take a look. And another one is certainly you're welcome to use my book, which is entirely online. So if I go to, once again, math01.com, let me click on it. So calculus book. So review of functions. So we are doing that's what we are, okay, differential calculus part 1. So that's what we're going to go through. But this is the review of functions, and as you can see, here it is. Chapter 2, operational functions, and you have algebra functions, functions that extract. Okay, we didn't talk about that, but certainly worth reading. These are short chapters, and at the end you have compositions and inverses. Okay, so that you might want to read it in the book. So is there a section in the previous section R, chapter R probably? I'm sure that you look at the book. It has 1,000 pages, so it has everything you can possibly want. And usually the review of the pre-calculus is included. Okay, so it is too bad that it is. Well, frankly, I just had never learned how to do compositions with Excel. It can be done, totally can be done. I just never actually bothered to do it, but you have to do it. The trouble is with that when you do a search, there is a command find, and it will find this one looking for one in this code. It can, but the trouble is that what it doesn't, then because the values are missing, usually it's not exactly the right one. So it just the illustration is not going to be that useful. So did you find it?
So it's pretty good calculus.
Pretty good calculus. It's there. So a lot of stuff is there. Okay, so this is the main thing about simultaneously nature functions, operations on functions including decomposition. The inverse is also kind of operations, except decompositions and all other operations. There are two components involved, and the inverses are it is one. You take one function and then you produce a new function from it. How? Well, you informally speaking, you interchange x and y. Okay, so you can imagine what happens to our graphs. Well, either one of these or here, as you can see. So the Excel knows which is the horizontal axis and which one is the second axis, the other axis. So if you flip, you can imagine a piece of paper that does that flip. Okay, so it is, you are, if you think about it, if you, that on the right, and suppose we want to take the, well, that function actually has no inverse, unfortunately, so, let me find a function that does. Well, then this one's fine. This one has inverse, it appears. It appears, well, hold on a second, let me, we do, okay, so I put, now first of all, you can see if I try to flip this one, the fact that it fails the horizontal line test. This one fails horizontal line test. If I flip it, what happens? It will, the result will fail the vertical line test. Okay, so that horizontal line will become vertical and it fails. Okay, so but if I have a function that is 1 to 1, so every horizontal line crosses the graph only once, then I'm flipping and it will satisfy the vertical line test and I'm all right. But you can imagine that this is a piece of paper. Let me try maybe. Another tool that good to use is Excel. Is Paint. Okay, so this is Paint. Is the it's another assessment. Let me make it larger. So Excel won't flip it, but this one will. So let me find. So there is a rotate option. So a rotate. Well, this is not what we need. This is 180-degree turn pretty much. This is not what we want to accomplish. So what we want to remember, we want to flip it about the diagonal, which is as if made of. You can think of it as if it is made of two pieces, two steps. So imagine that there is a diagonal. Okay, there is a diagonal here. Okay. And I want to flip about the diagonal. So then I grab it by two pieces, by two ends of the diagonal, and do this. Notice that we're looking at from the wrong side. Okay, so that's the flip. And as you can see, there are no operations in Paint to do that, but we can do it in 2 steps. Do you see what steps we can do it?
Flipping it vertically and horizontally.
Then it's first vertical, then horizontal. So, no, hold on a second. That's not that obvious. If you flip vertically and then horizontally, that's not it. It is in fact a rotation followed by a flip. Let me see if I'm sure I'm positive which is rotation. So, rotation saying if I rotate 90 degrees. Like this, and then flip. Yeah. See, the diagonal, it looks the same, so that's the sign. So let's try to do that. So I will rotate 90 degree right, and rotate 90 degree right, and then I flip vertically, like this. Okay? I should have kept the, well, you can compare with the original. So this new graph compared with the original here. Okay, you see how it has been indeed flipped above the diagonal, right? So once again, it is more complex graphics and more troublesome this operation is. But once again, remember it can be carried out like this. Okay, draw it on a piece of paper, flip it, and then look to the light, you'll see in the shape of the graph, or use Paint. Use Paint. Also, certainly Excel, it's really no challenge for Excel to flip exercise. Well, let me just quickly see if it is actually possible to flip the. There might be. There is a must. Unfortunately, this is Windows 10, but I think there is some other operation which is literally says interchange the axes. So if I take this, there is somewhere.
Switch row column.
Yeah, okay, you're good. Oh, no. No, I don't think so. Okay, so I was just wrong. It is, it's not that, Oh, no, no, not switch row and column, yes, not switch row, switch columns. Okay, so that's not it, unfortunately. Okay, so, let's try to wrap this up. Any questions about this material? So, just keep in mind that you will have to do some reading in order to make the homework easy. It's not complicated if you got these concepts. Even if you don't remember the ideas, if you just have some general understanding of what's going on, which I tried to review here, you should be all right. Just we can talk a little bit more about that tomorrow. So let's figure out what's missing. Okay, so let's finish early today because we didn't take a break. Okay.